right. Today we're diving deep, I mean really deep, into the heart of matter itself. We're going to a world that's so small it's almost impossible to imagine, but it holds the keys to, well, everything. We're talking about atoms, nuclei, and radiation. Let's get into it. So when I say the word atom, what do you picture? Come on, be honest. Is it that little solar system model with electrons whizzing around a center like planets? For a long time, that's not what scientists thought at all. And the story of how we actually found out its true shape, oh, it's one of the best plot twists in the history of science. You see, before about 1910, the best idea anyone had was something they called the plum pudding model. Seriously, the idea was that an atom was kind of like a hazy, positively charged blob, that's the pudding, and scattered inside were these little negative electrons, like plums. It kind of made sense at the time, but it was about to be proven completely and spectacularly wrong. And what changed everything was an experiment that, on paper, should have been pretty straightforward. It just involved shooting some tiny particles at a super thin sheet of gold foil. But the results? They weren't just a little surprising. They completely demolished the old model and forced us to build a brand new picture of the atom from scratch. And that brings us right to this first major breakthrough, the legendary gold foil experiment run by Ernest Rutherford's team. This is, without a doubt, where our modern understanding of the atom was born. So, here's the basic setup. They took a source that fired off a stream of what are called alpha particles, which are basically just tiny positively charged bullets, and they aimed them at an incredibly thin sheet of gold foil. And why gold? Well, because you can hammer it out to be ridiculously thin, just a few atoms thick. Now, based on that whole plum pudding idea, they expected this to be pretty boring. They thought those alpha particles would just sail right on through. I mean, if the atom's positive charge was all spread out and mushy like a pudding, there's nothing solid enough in there to stop these little guys. But what they actually saw was just mind-blowing. Yeah, most of the particles did go straight through, just as they predicted. But some of them got knocked sideways. And, get this, a tiny fraction, about 1 in 8,000, bounced almost straight back at them. Rutherford famously said it was like firing a cannonball at a piece of tissue paper and having it bounce back and hit you. Just unbelievable. So these wild results could only mean three things. First, since most particles went right through, atoms must be mostly empty space. Second, for something to bounce straight back, it must have hit something incredibly small, but also incredibly dense and massive. And third, since the positive alpha particles were pushed away, this tiny little center, which they named the nucleus, had to have a positive charge too. Just like that, the plum pudding model was toast. Okay, so we've found this tiny, dense, positive thing at the heart of the atom. Now let's zoom in. How do we describe what's going on inside this nucleus? Well, it really all boils down to two very important numbers. First up, you have the proton number, which we call Z. This is the atom's absolute identity. It's its fingerprint. If it has 6 protons, it's carbon. If it has 92, it's uranium. End of story. Then you have the nucleon number, or A. This is just the grand total of everything inside the nucleus, all the protons and the neutrons added together. This number basically tells you how heavy the atom is. And lucky for us, scientists have a really clean and simple way to write all this down. You have X for the element symbol. The number on top, A, is that total mass number, the nucleon number. And the number on the bottom, Z, is the proton number that defines the element. So with just these few characters, you know exactly what kind of nucleus, or nuclide as it's officially called, you're looking at. And this system immediately brings up a really cool concept. Isotopes. See, you can change the number of neutrons in a nucleus without changing the number of protons. For instance, every single carbon atom in the universe has 6 protons. But carbon-12 has 6 neutrons, while the famous carbon-14 has 8 neutrons. Same element, different weight. That's an isotope. So protons, neutrons, isotopes. Why does all this matter? Well, this is where things get really dynamic. Because it turns out not all combinations of protons and neutrons are stable. Some are just wobbly. And this instability is the true origin of radioactivity. Think of it like you're building a tower with blocks, but you've stacked them a little too high or a little off center. It's shaky. To keep from toppling over, you might need to toss a block off the top. An unstable nucleus does basically the same thing. It ejects a particle or a burst of energy to settle down into a more stable arrangement. And that whole process is what we call radioactive decay. And this decay releases radiation, which usually comes in 3 main flavors: First, you have alpha particles. These are the heavyweights, big, chunky helium nuclei. They can be stopped by a piece of paper, but they pack a big punch over a short distance. Then you have beta particles, which are essentially just super fast electrons. They're a bit more nimble, can get through paper, but are stopped by a thin sheet of aluminum. And finally, you have gamma rays. These aren't even particles, they're pure energy, like superpowered X-rays. They have no charge and are incredibly tough to stop. You need thick lead or concrete for these guys. Now, you might think this whole decay thing sounds pretty chaotic, right? A nucleus just randomly falls apart. But here's the thing, it's not. While it's unpredictable for any single atom, the process itself follows very strict, predictable rules. It's like cosmic bookkeeping, and the books always have to balance. Let's look at an alpha decay. We start with thorium-232. It's unstable, so it kicks out an alpha particle. That's the helium nucleus. Now just look at the math. The mass number on top goes from 232 down to 228 because it lost 4. And the proton number on the bottom goes from 90 down to 88 because it lost 2. See? The numbers on the left perfectly add up to the numbers on the right. The books are balanced. Okay, now for beta decay. This one's a little weirder. You have an unstable radium-228 nucleus. Inside it, a neutron actually transforms into a proton. To keep the charge balanced, it has to spit out an electron. That's our beta particle. Now look at these numbers. The mass number, 228, stays exactly the same because we just swapped one particle for another, but the proton number goes up by 1, from 88 to 89. We've literally transmuted radium into a whole new element, actinium. How cool is that? So all this talk of radioactive decay and radiation can sound, a bit intense. But the reality is this isn't some strange process that only happens in a lab or a power plant. It's a completely natural and fundamental part of the world we live in. From the very ground beneath our feet to the air we breathe, and even the food we eat, we are constantly surrounded by a low level of natural radiation. We call it background radiation, and it's been a part of planet Earth since day one, long before we ever were. So where does it all come from? Well, you get a little bit from cosmic rays zapping down from space. You get some from medical stuff like X-rays. You even get a little bit from inside your own body, from elements in the food you eat, like the potassium in bananas. But just look at that huge slice of the pie right there. Yeah, more than half. 51% of the average radiation dose we get comes from a single source, radon gas. It's a natural radioactive gas that just seeps out of the ground from the natural decay of uranium and rocks and soil pretty much everywhere. It's colorless, odorless, and it's the single biggest contributor to our daily dose of radiation. So let's wrap up with this thought. We started by asking what an atom looks like, and we ended up in this incredible place. We discovered that an atom is mostly just empty space, but at its heart is this unimaginably small nucleus that dictates what an element is, how it behaves, and can release the incredible energy we call radiation. It just makes you wonder, right? What other fundamental secrets are still waiting for us, locked away deep inside that tiny, powerful core?